Good afternoon, students. So welcome back to our online session. In today's sessions, we are same continuing these problems related to the Butterworth filter. So here, the previous question we have just have the question: design the Butterworth filter, IIR low pass filter, that is digital, by using the bilinear transformation technique. So here the gain is what? 0.6 to maximum is 0.1, and the frequency is what? 0.35 pi to 0.75, right? So t is given as 0.1 second. So if you draw the graph for low pass filter, it allows the lower frequency to attenuate the higher frequency. This is the practical diagram of low pass filter. Here we do have AS is equals to 0.1, that is nothing but the gain of the stop band. What about the gain of the pass band? It is what? 0.6. We both the values we had, omega p is 0.35 and 0.75, right? So first thing we have to find the order, right? So how do we find the order? In order to find AP and AS, we have 10 power minus whatever the value is there into dB per 20. We have to do it. We'll get the answer as 0.6 and 0.1. Clear? So already they gave in the question, so that's what we are substituting. If they won't give, then we have to use it this one. If they gave pass band ripples and stop band ripple, if you apply this one, we can apply this way. The question can be asked in that way and in this way as well. So the first step is what? Find the equivalent analog frequency by using the bilinear transformation. How do we find the analog frequency? So omega p, analog frequency of pass band, is given by 2 by t tan of omega p by 2. So we do have omega p, we write in radian per second. That is in degrees, so we are converting into radian by applying this formula, right? So we get omega p and omega s. Next thing, we have to find the order. So if we substitute this value, log to the base 10 1 by a square minus 1 by 1 by ap square minus 1, log of omega s by omega p. If you substitute both the values, like we had a square is what actually, students, so we got it as 100, and ap we got it as 2.77. if you take reverse of it and if you do the square for that, like this one, 1 by 0.1 whole square, I can write 0.1 into 0.1, that is nothing but 0.01. If you take a reverse of 1 by 0.01, I can write as 100. Similarly for the second one, 0.6, so 1 by 0.6 I can write as 0.6 square. So 1 by 0.6 square, nothing but 0.6 into 0.6. So that will be 1 by 0.36. If you take that one in terms of numerator, we got it as 2.77. Clear? So if you divide both omega s by omega p, we got it as 3.203. If you divide both things in terms of log, here log is the log of this, we got that, and we got n as this. Next thing, we have to find the transfer function, right? So what is n? N is even, right? So we can substitute k is equals to 1 to n by 2. That means 2 by 2. 2 by 2 will be 1 only, right? So we got only one term. So bk, what is k value now? 1. So 2 into 1. 2 ones are 2 minus 1. So 1 only. So 1 pi by 2n. What is n? What is n value we got, students? Small capital N. Order is 2. 2 to the 4. So if you have substitute that, we got it as 1.414. This is our transfer function h of s. 1 by sn square plus, what is this? Bk into sn plus 1. What is bk value we had? Bk is 1.414. We substituted that, we got the answer. Next thing, find the analog cutoff frequency. How do we get the cutoff frequency? Omega c is equals to omega s by 1 by as. If I am taking the stop band, I need to use this stop band. So 1 by as square minus 1 whole power 1 by 2n. So n is what? 2, 2 2s are 4. Right? We got n what? What is our n value? Order. We got the order as 2, right? So approximately value we take, right? This is capital N, that is order 2. If you substitute that order in this equations, we can able to write that answer as 1 by 0.1 square minus 1, 1 by 4. If you do it, if you simplify, you got 12.44 radian per second. That is the cutoff frequency in analog form. Similarly, next thing, we have to find the step 5. How do we find step 5? We have to find the unnormalized transfer function. How do we get unnormalized transfer function? Wherever s is there, we should divide it by critical frequency. Sn is equals to s by omega c. So s as it is omega c, this will be 12.44. If you take 1 by 12.44, you will get as 0.08. So wherever s is there, I will substitute it. In Sn square, I got 0.08 s square plus here also we do have Sn in this equation. In this particular equation, right? Sn. That Sn value I am replacing with omega c. Similarly, we got this as actual answer of our transfer function. Till here we found h of s, but our question is what? They asked to find thus s domain into z domain by using bilinear transformation. So what is the bilinear transformation is all about, students? How do we find? S tends to 2 by t, 1 minus z power minus 1 by 1 plus z power minus 1. So wherever s is there, that could be replaced by this particular factor. 2 by t, what is t? 0.1. 2 by 0.1 is nothing but 20. 20 into 1 minus z power minus 1 by 1 plus z power minus 1. So wherever s is there, in all the points you have to substitute. This is s, this is s, this is s, right? So those s factor we need to replace this. So see, here s is there. So that's what we wrote it. Previously what we had in this as you can see here, in this what we had, s square, right? So s will be 20 square. 20 square will be 400. The 1 minus z power minus 1 by 1 plus z power minus 1. And similarly 17.59, the previous number was there as it is. We have put it. And then s value is what? 1 minus z power minus 1 by 1 plus z power minus 1 into 20. So 20 into this factor you will be getting as 351.8. This is as it is. Take a LCM, cross multiply a minus b whole square here. Here also a minus b whole square. If you cross multiply a square plus b square minus 2ab. Here also a square plus b square minus 2ab. Whole denominator we are shifting in the numerator. So the numerator will be a plus b whole square. So a square is 1. 1 into anything will be 1. B square is z power minus 2. That is as it is. Plus 2ab. 2 into z power minus 1. So 2 into 754.75. If you multiply, you will get as 309.5. So in upper side, a plus b whole square. They are actually writing b square first. B square plus 2ab plus a square. 1 square. That is nothing but 1. 1 into this will be as it is. Clear? In denominator you have to simplify. Wherever 1 is there, here 400 plus 351.8 plus 154.75. If you add all that thing, we will get it as 906.55. Then take z power minus 2 common. Here is what? 400. Here z power minus 2 is. Multiply with this minus 351.8 if you subtract. And then you have to add 154.75. You got it as 202.95. How we are doing? We are taking z power minus 2 common for the first factor, and for the second factor z power minus 1 common. We can write this answer as 154.75 z power minus 2 plus 309.5 z power minus 1 plus 154.75. In the that would be there in the numerator, and in the denominator, what is the value we get it as? In the denominator we got it as 202.95 z power minus 2 minus 490.5 z power minus 1 plus 906.55. Clear? If I want to further just want to write down what I am doing, I am just dividing this whole term by this factor 906.55. Why I am doing? Because I want to write in denominator as 1, right? That's the reason I am dividing numerator and denominator by 906.55. So what is the first term here? 154.75 divided by 906.55. If you divide that, I'll got it as 0.1707. If you divide 309.5 by 906.55, you got this. Similarly, for this also we got this. And denominator 202.95. If I divide by 906.55, I got this for this factor. And 906.55 divided by 906.55, I got it as 1. That means this factor I want to eliminate. So in order to eliminate, I have divided by this 906.55 in numerator as well as in denominator. So basically, what's the meaning of transfer function? Transfer function is all about h of z, right? H of z is nothing but output by input. So what is the output value? Y of z, input value x of z. So output by y of z, input x of z. Cross multiplied, this in y of z will come here, x of z will come here, right? This is nothing but the output value, y of z. We wrote it. And y of z as it is, remaining all you shift on right side. Multiply with y of z, 1 into y of z, 0.54 into z power minus 1, minus value shift there, it will be here, right? There is this here, 0.54 into z power minus 1. This is minus, no? We are shifting on right side. Similarly, 0.224 into z power minus 1 into y of z, that we are writing here. It will be plus. If you shift that side, it will become minus. Similarly, x of z multiply with first. It is there with first, it is there with second, it is there with third. So what I am writing? I am writing in ascending order. Z power 0, z power minus 1, z power minus 2 for x of z, then y of z. If they ask to find the direct form of realization, that is most important. They will definitely give not only for this one problem, you can stop, the answer is here also. If they ask only the transfer function, if they ask to realize, if they ask to write that blocks for that, we have to draw its diagram. How do we draw it? That is important, the blocks. There are two forms to draw that one. One is the direct form 1, another is the direct form 2. So direct form 1 and how do we design the direct form 2? That both the things you have to know it and you should draw it properly. So if you draw that one, how can I draw it? I had y of z, right? That is the output. That should be the output y of z. And what is the input value I do have, students? Input is x of z, right? How do we design x of z? This is my x of z. First term what I have 0.170. That is the first as it is. Second what we had 0.341 is the second one. Then third is what 0.1707. This is still x of z. These all are x of z value, right? So in the first one, do we had any z power minus 1? No. That's why it is directly passing to the summer. So you already have learned this in control systems. The same concepts we are just using to design the block. So first thing, x of z multiply with this factor 0.1707 into plus sign, that will be as it is. Similarly, x of z multiply with z power minus 1. If you can write that one, what is the second factor we do have? 0.341. 0.341 into z power minus 1 will be same. 0.341 to z power minus 1 into multiply with x of z. This will be there. Then between these two terms, what is there? Plus is there. That's the reason we are writing as summer. Clear? The third term, what is there? Z power minus 2. How do we get z power minus 2? Here we had z power minus 1. Here we do have one more z power minus 1. If you multiply this 2 will be z power minus 1 into z power minus 1. It will become z power minus 2. Clear? So that's what it is written here, z power minus z power 1 separately, because already we do have. So we are just writing only once. So this will multiply this 2. It will become z power minus 2. And what is the multiplying coefficient is there? 0.1707. So that we kept as it is. That we wrote it here. And then we multiplying that term with the x of z. So if you multiply this whole thing, and if you adding this thing, this still here, we completed the x of z. Right? Similarly for y of z, how do we write? Tell me how many terms is there in y of z? 2 only, right? What is this 2 terms? 0.54 is the first term. So we wrote it 0.54. It is there with plus sign. So we wrote it at plus here. And z power minus 1. It's z power minus 1. Do we have constant here? No. The previous one we do have a constant, no, without z power minus 1. That's why here one more term came. Here we had only 2 terms. See? This is first term, this is second term. That's what we are only writing the 2 terms. So this is the we can write direct form of realization. Very, very important. If they directly give this question also, they can ask you to design the direct form 1 realization for these functions. For sure, you will get one question for 5 marks. Definitely, if you practice one, that means you are done with the 5 marks. You will be there, that 5 marks in your pocket. Thing is that you should practice this blocks. Clear? So what we did from starting? First, from the starting of the problem, let me just go ahead and just take a recap. What else we just wrote it in this? First thing, they gave a question that find the, this can be the question, design a Butterworth digital IIR low pass filter using bilinear transformation by t is equals to 0.1 second. So that is the question is given with the following specification. Specification is also given. Passband ripple is delta p, right? That is 4.436 dB. In that decibel it is there, we have to write in 10 power anti-log. So that's what second thing is given. Stop band attenuation in dB, decibel it is greater than or equals to 20 dB. Right? This is alpha s, this is alpha p. Right? So omega p and omega s we do have, that is also given in that question. This also you can take it. 0.35, it is radians per sample. We have to write in radian per second. Clear? That's the reason we are converting. Second thing, omega s is also there in 0.75, that is in radian per sample. We have to convert in radian per second. In order to do that, first I have to find that gains, right? AP is equals to 10 power minus whatever the decibel is there divided by 20. Because always we'll write 20 log 10, right? For the decibel, if you want to take an anti-log, that will become 10 power of that factor. Clear? So that's what we have converted into decibel. Sorry, decibel to that given gain. So AP we found, AS we found. Both the values we got by substituting 4.436 divided by 20 with minus. We got this term and the second term as well. Clear? Next thing, omega p and omega s, it is in what? Radian per sample. We have to write in radian per second. So this is a formula for writing the radian per second. So we wrote it in terms of radian per second. Similarly, the second step is to find n. So we substituted all the values and we got it as greater than or equals to 1.707. Here is mentioned equals to, it's not equals to, it is greater than or equals to. Okay. So whatever the value we do have, that should be greater than or equals to the given factor. So what is the factor here? We do have factor is 1.7307. So that if you want to write more than that, what could be the value? Obviously it should be 2 only, approximately equals to 2. That's what we wrote as 2. So 2 is what? Even, right? So we have to find the transfer function. How do we find transfer function? H of s. H of s can be substituted by this formula with pi is equals to k is equals to 1 to n by 2. What is n now? N is equals to 1 sample. So we substituted that 1 sample and we can write this function. What is bk here? Bk is equals to 2 into sine 2k minus 1 by 2n of pi. So same thing. What is the k value we do have? K value starting from 1 to maximum is 1 only. So b1 is equals to 2 into sine 2 1s are 2, 2 minus 1 is 1. So pi by 2 2s are 4. So pi by 4 of that factor will be 1.414. Then later on we have to substitute it the critical frequency omega c. That is omega c is given by omega s by 1 by as square minus 1 1 by 2n. So what is n value we do have? N is equals to 4 samples. So we have put this over samples. We can write critical frequency as 12.44 radian per second. After finding that factor, next thing is that we have to substitute h of s. How do we get h of s? By Sn of n, where is n value? Whatever the s is there, that should be divided by critical frequency. So the same thing, we substituted the critical frequency in the given formula. After substituting the critical frequency, we can able to find out h of s. Wherever the term is there, we have replaced. What is the next thing? Till here we have done with our answer. If they ask only to solve this, till here we can do it. But if they ask further, like finding the bilinear transformation, we have to proceed ahead. That means we have to find h of z as well. So we know that for bilinear transformation, it is 2 by t, 1 minus z power minus 1 by 1 plus z power minus 1. So I can write in this way, or else I can write 2 by t, z minus 1 by z plus 1, anyone. So I am using this formula. What is t now? 0.1. So 2 by 0.1 is 20. The same factor wherever s is there, I have replaced, and I got this is my transfer function. Right? After that, what is h of z value we had? Output by input. Output is y, input is x. Output by input, we wrote it and we see further simplified. We can able to write its block. So this is how the complete answer of our Butterworth low pass filter with digital analysis part we did, and we try to convert into analog form as well. So this is how the complete answer has been obtained. Likewise, we do have a next problem that is also given the same concepts here. It's mentioned that design a Butterworth digital filter IAR high pass filter using the bilinear transformation by using t is equals to 0.1 second to the satisfying the same condition. See here, this is 0.6, maximum is 0.1 and 0.75 to 0.35. So we know for high pass filter we should design it. What is a high pass filter is all about? It allow the higher component, it resist the lower component. That's what the lower component is attenuated, higher component is given. And gain is also given. Pass band is 0.6, stop band is 0.1. Frequency in the stop band is 0.35 pi, which is the lower. Out of that, we have to select. In the question it won't mention which is the frequency of pass band, which is the frequency of stop band. You have to design it. You know that high pass filter will have this specification. Clear? So we substituted all the factors and we can write the high pass analysis. This is for low pass, right? Reverse, if you take it for high pass, we can design that one. So we know that omega s by substituting is 2 by t tan of omega s by 2. If you take it in terms of the given specification, we are designing what the question they mentioned. This is for high pass, right? So what we are doing, specification should be converted into IR low pass first, so that we can easily design that. That's what we are writing as AS and AP. So what is omega s? We can write this is 2 by t tan of omega s by 2. So this will be what 39.25 radians per second. This is also omega p 12.256 radians per second. Next step 2 is to find order. Already we did in a previous problem. No, order will be same. We won't change, get the order. Similarly, we find h of n. Substitute omega c. The previous one, how we did, the same thing we'll get. But this is the most important thing what you have to remember. For high pass filter, we'll write h of s as omega c by s naught s by omega c. That is the important thing you have to remember, because we are writing for the high pass, right? This step you have to remember while we are designing the high pass filter. So this is, we wrote it. High pass filter we can replace, and we can write as wherever term is there we can replace with s square. Take the LCM. So if you take the LCM, what is going to happen? This will be come in the numerator, and there is no s here. It will be s come over there. This still here what we did, we have found h of s. Now what is asked in the question? They asked to find its response also. For finding the response, we are using the bilinear transformation. Bilinear transformation, what is the formula for it? h of z we can write as h of s, where s tends to 2 by t, 1 minus z power minus 1 by 1 plus z power minus 1. So t is what? 0.1. So 2 by 0.1 is nothing but 20. So we substitute this in this s value wherever s is there. Here is s square is right. So 20 square will be 400. The s value we substitute, here is also s is there in the first term. This one I am telling last term. So this last term we are writing in this way. So this last term as it is, wherever s is there, we replace with that function. After substituting, after simplifying this whole term, already I have shown you how to simplify the terms, right? So whatever the terms we do have, we can replace by using this particular transformation techniques. So we can substitute this whole thing, and again the same analysis part you have to do it. Clear? X of z and y of z. So what are the z? How many there? With x, z power minus 2, z power minus 1. So one term, second term. First term z power minus 1 is 0.882 with minus. So we put it minus. For the second term 0.441. Till here it is x of z. And y of z, it is also have z power minus 1 and z power minus 2. Z power minus 2 had with minus. That's what it is. Sign kept here as minus 0.224. So we put the values for both the things in this way, and we can find y of z. Clear? This is the direct form 1 we did with the realization. So direct form 2 also we can do it, student, with the same problem. What we have to do it? Only thing is we have to add a weighting sequence. That's it. If you add the weighting sequence for the given problem, this is the direct form 2. What is the output? Y of z. This is the output, no? This is the output y of z, right? X of z, y of z by x of z we are writing as this term. 0.441. After simplifying, you do it. Already the steps are here. And the previous also I've said you. If you do it that same thing, we can write the answer in this way as well. So y of z by x of z. So y of z by x of z I'm writing as reverse. That is nothing but 1 by reverse of this. Only the denominator parameter. So if you do it, if you multiply with that, we substitute it separately with y of z. This is your the y of z we are replacing it w of z with x of z. This we have did separately, and for y of z also we are multiplying with w of z. If you multiply both w of z cancel, y of z by x of z only you will get. But why we are adding weighting sequence? In order to obtain the answer in a sequence form. So for getting that one into particular sequence, we are doing in this way. So we got y of z, middle is what? Weighting sequence. What is the first thing? This is for x of z, no? What are the values? 0.224. We wrote it here. 0.224 with z power minus 2. And second, minus 0.4541. Here is what? Minus 0.541. Only one block is there. This is called direct form 2. Okay. So we are just finding with respect to direct form 2. In between, w of z is there. This is for y of z. 0.441. 0.441, 0.441 minus 0.882. Clear? This is how we can do it for direct form 2 as well for that particular realization. Clear? So we just need to thing is that we should know how to proceed with the problem. What is the difference between low pass and high pass? What is the difference with that? In low pass, critical frequency whatever we do have, omega c by s we will do in low pass. In high pass, s by omega c. That only the term which is differed in both the things. So we should be very clear while we are just taking the value for low pass and high pass. Clear? So this is the steps you need to adopt it in order to simplify the IIR Butterworth filtering with respect to the low pass as well as with respect to the high pass kind of filtering. Next thing what we need to learn is we have to learn about Chebyshev. So what is the next step we are going to learn is Chebyshev approximation techniques. How do we get that Chebyshev basically? So before that we should know that whatever the value till now we get n is equals to even, no? If at all your n value is odd, only this h of z will be changing. That what we are adding with odd 1 by sn plus 1 we are adding, and we are just writing the answer as it is. Clear? This is the way 1 by sn plus 1 pi of k is equals to 1 to n minus 1 by 2. The same term we can write it over here. Next thing, bk will be same thing, only the thing is odd means this will change. Next method is for Chebyshev approximation method. So for Chebyshev we do have students two methods. One is a type 1 and type 2. So basically what is a Chebyshev filter? The analog Chebyshev filter is designed by same approximating the ideal frequency response using an error functions. By using the error functions we can able to find out their analysis as well. That there are two types in it, type 1 and type 2. We are going to learn details about it, how the type 1 is used and what are the things we should consider in type 1 and what are the things we should consider in the type 2 in the next section. Okay, so this is about the today's session. So make a note of it, all the points whatever we discussed in today's sessions, and tomorrow's sessions we are going to learn further. Thank you.